Give it a sec. All right, so we're going to start off with water, or water if you're not from the Boston area, but I like water because, it's Boston. And let's start off with this quote from one of the most influential men of American history, Benjamin Franklin. And Ben Franklin says, "We know the value of water when the well runs dry." And I really think that's an absolutely fantastic quote by Ben Franklin, because we sort of can preface this by asking a few questions. That I don't expect anyone to answer, but just sort of think to yourself: have you ever worried about the quality and the accessibility of your water? And do you ever really think about how much water you consume, either directly or indirectly, on an everyday basis? And Ben Franklin's quote really sort of gets at those two questions, because unless you had to really think about those two things, the average everyday person in the United States and in Europe, they don't really have to think about their water, the quality of the water, where their water is coming from, or anything like that. And the reality is, it's not something that Americans have ever really thought about, at least since, at least in a large sense, since the Dust Bowl in the early 1920s. So I'm not in the early 1920s, in the 1920s. And so water isn't really something we think about, but as I'm sure you guys probably know, the average human is about 70% or so of just water. So clearly water is an important part of our average everyday life. For those of you that are interested in NASA, you know that when NASA finds water on Mars or the moon or anything like that, it's a big deal. Now, why is it a big deal? Well, as we'll discuss today, water is the biological medium. It makes life possible. So wherever there's water, we know there's life. And that's kind of the cool thing. But water is, because it's essential to life, it again is an inescapable part of our reality, and it's super duper important. And how much water we use might surprise you. So on a typical average every day, your average American consumes about 80 to 100 gallons of water. Now you might think, wow, that's way too much. I don't consume that much water at all. But the reality is, consuming water, you don't drink 80 gallons of water a day, right? Your average person can't drink more than a half a gallon of water per day. But the reality is, the stuff you do, showers, washing dishes, washing your clothes, watering your gardens, right? Watering the lawn, even the food you eat, all required a massive amount of water into it to physically make it work. And that's where it really starts to add up. In particular, it really starts to add up when we start to think about our food consumption and our food choices. Now, the reality is, water scarcity is a big problem. Water insecurity is a big problem. Flint, Michigan is a great example of this, where they have some pretty severe problems with water security. Due to the sort of the outdated nature of their water infrastructure. But regardless of where you go, water is a problem, whether it's too much water. So I'm sure you guys probably saw all the crazy floods that are happening in Central Europe right now, including entire towns in Germany basically being drowned out by massive floodwaters. Or maybe you saw earlier this year where the Italian parliament was completely flooded by storm surge. Water is an average everyday concern across the globe, whether it's too much or too little of it. But the reality is, more than 3.5 million people die each year globally as a result of contaminated water, which is really sort of a lot. I mean, when you think of sort of how bad COVID is, it's still not 3.5 million people dying each year. We've lost about 2 million people to COVID, and water problems alone have killed 3.5 million people this past year. So water contamination is no joke. But more importantly, about 1/5 or about 20% of the world's population does suffer for some water scarcity. And that isn't just something that happens in Africa, it's something that happens globally. So let's talk about an interesting case about water. Now, we'll talk about Cape Town in South Africa. South Africa's has a particularly interesting history, both recent and in the past. But Cape Town, South Africa, is a relatively sizable town. There's about, or I should say, a city. It's called Cape Town, but it's obviously a city. About 4 million people live in there. Now, they suffered about a 3-year drought that reduced their water reservoirs to about 25% capacity. Now, in 2018, governmental officials there warned that if levels dropped below less than 14%, the government would actually physically shut off residential taps and ration about 6.5 gallons of water per person per day, which seems kind of crazy to think about. But as we'll discuss in climate change later in this semester, it's really not a not a out of this world thing to think that it might happen elsewhere as well. It's kind of amazing. Now, in South Africa, residents did respond by restricting their water use by about 50%. So they cut their usage in half, about 210 gallons per person per day, which allowed them to escape this sort of 14%. But you can think of a country that is on a continent that is sort of mired in water issues, but you could think of a country that isn't typically mired in water issues, facing water issues and responding in a way to save their own water. So I think it's a really interesting case in Cape Town of what we sort of see about places that aren't normally water scarce, but when they become water scarce, what physically needs to be done to fix that water scarcity problem. Now, let's talk about this concept of embedded water, because the average American consumes about 8,200 gallons of water per day, but that's clearly not something you drink, right? So just to put that in perspective, if you were to drink 100 gallons of water, that would be 800 pounds of water, which is a lot of water, right? So clearly not something we're drinking. So where does the rest of the water come from? And the reality, the rest of it comes from what we call embedded water, which is a term we use to describe produce or products that we consume that require some substantial amount of water. Now, I love this little chart over here because it's a really fantastic look at how much water goes into making things that we use on an average everyday basis. Now, just to put this in perspective, some of the most water consumption heavy pieces of things of your life include coffee, which most people drink on an average everyday basis, which requires about 132 liters to produce one single cup of coffee, about 125 milliliters. So lots of water goes into feeding the coffee tree to produce coffee beans, which then can be roasted and put in your cup to drink. So again, a substantial amount of water to one of the most commonly drank beverages on the planet. However, if you contrast that to one of the other most commonly drunk beverages on the planet, which is beer, beer requires substantially less. So about 74 liters of water is required to produce 250 milliliters of beer. So if you're trying to be green in terms of your drinking, you should be like our friends in the yes, drink beer, not coffee. So if you're trying to be green, you should be like our friends before the sort of the mass production of coffee. Drink beer for breakfast and not coffee. And if that's not the most college-friendly slogan I've ever created, I don't know what is. So if someone ever questions why you're drinking beer, you just say you're being environmentally friendly because you're not drinking coffee. But the reality is lots of other things consume a lot of water, in particular the production of livestock. So pork, beef, chicken, all require substantial investment of water, as does the production of chocolates. Chocolate requires a lot of water, which always surprises me because of, chocolate is consumed a lot, but it just always surprises me that chocolate does require so much water. Because then again, on the other hand, it's relatively closely related to coffee, so it probably shouldn't surprise me too much. So it's pretty cool. Sort of that breakdown. I hope this chart was helpful for you to sort of see that embedded water idea, really sort of how your dietary choices affect this sort of 80 to 100 gallons of water idea that we see. Now, where is all the water on Earth? Now, typically speaking, you lose about 2 to 3 liters of water per day from sweating, exhalation of water vapor, so from your lungs, and breathing, as well as just the secretion of waste, both hard and solid and liquid waste, which is kind of, when you think about it, it's a lot of water, but given that you're 70% water, it's not overly surprising that you lose about 2 to 3 waters a day. Now, clearly, this 2 to 3 liters of water, it can be higher if you do a lot of strenuous exercise, so you're sweating a lot. It can also be lower if you're very, very sedentary. But on average, it's about 2 to 3 liters of water. Now, the planet itself is covered in about 70% water, but as you guys probably know, the oceans account for about 97% of all water on this planet, which is staggering, but not unsurprising. Now, the collective reservoirs, both fresh and salt water, are what we call the hydrosphere. So to break that down, hydro is water, sphere is sphere. So our sort of the hydrosphere is all the water on the planet as a whole. But you'll notice that of the water on the planet, about 2.5% is fresh. The other salt water, just to let you guys know what that is, other salt water is typically like salt lakes. So for instance, the Great Salt Lakes out in Utah and Nevada and places like that, or maybe the Dead Sea. So places that are not ocean, but are very, very salty. Now, of the fresh water, that 2.5%, about 70% of that is stuck in ice caps, snow permafrost, as well as glaciers. And then about 30% of that is underwater. I'm sorry, underwater. Of course, it's underwater. Underground. Now, what does underground mean? It just means water that is flowing through our soils underground, not accessible directly to drink out of, say, like a river. Now, of that fresh water, you'll notice that 0.4% is other fresh water. Now, where does that come down to? Well, lakes are by far the most common source of our fresh water, then rivers, water that's trapped in the upper layers of soil, water vapor in the atmosphere, water in living organisms, which I think is a pretty cool number, about less than 1%, and water in swamps. So of all the water on a planet, a tiny fraction of it is found in places that are readily accessible by man, which I think is absolutely remarkable when you think about how much water on the planet is, how much we rely on to support our average everyday human lifestyle, how little of that water is physically accessible to support humans and other biological life, which again, will never cease to amaze me how little water is available to humans, despite how much water is on this planet. So it's kind of a fun graph. I hope if you've never seen this before, this really puts into perspective how precious water is as a resource. Because again, of that 2.5%, fraction of that 2.5% is actually water that is accessible. It's kind of an amazing thing. And if we think about sort of the greater Boston area, we get most of our water from the Quabbin Reservoir, which is just a big lake. And we think about the Boston area being solely dependent on this one small water source of lake water. So it's kind of an amazing thing when you think about it. So where is the water on Earth? Well, clearly the most of it is in either in the ocean, which again, most of it is, but a huge amount of it is underground, inaccessible as ice and snow caps. So let's talk about where water goes, how water is cycled. So I think this figure does pretty nice job of sort of talking about those things. So we have rainwater, as well as you can think of snow as well. It's just hard water, right? Where we have rain essentially evaporates from our soils, evaporates from our rivers, lakes, streams, whatever, or the ocean, goes into the atmosphere, hangs around, forms clouds, and those clouds rain precipitation down on us. Now, of all the rain that falls onto the planet, about 75% falls onto the ocean, which is pretty impressive. And the reality is, most of the water that's in the ocean hangs around the ocean for a very, very, very long time. So the average, what we call the residence time of water in the ocean, is about 3,000 years, which is a pretty, you think about that, the 3,000 years ago, it was back when the pyramids were being built, right? Or close to that area, right? So water in the ocean hangs around for a very, very long time. Now, once precipitation falls, it goes into our streams and lakes and stuff like that, but a lot of it doesn't actually make it into our bodies of water. It actually will seep through into our bedrock, into our soils, and eventually collect in aquifers. Now, aquifers are just subsurface areas of rock or sediment where water can accumulate and slowly pass through into oceans, rivers, lakes. And when we think about sort of why we care about aquifers as a source, for those of you that have well water, well water is people tapping into underground aquifers to draw up water for their own use. But aquifers and groundwater as a whole move very, very slowly, about 1 foot per year, so not very fast in terms of flowing of the underground water. It's not like a big river or anything like that. It's just a very slow movement through our underground channels. And I hope this sort of the final thing this diagram illustrates is how connected everything is. As you guys probably know, all rivers drain to the ocean at some way, shape, or form, and that everything is ultimately connected. So something that happens in a river has the potential to impact the ocean. Something that happens to the aquifers can impact rivers, and so on and so forth. So the water on this planet is really, really really connected. But again, here's a nice little sort of back and forth here between the water and the land, because again, evaporation via heating up by the sun puts things in the atmosphere, which causes things to rain. So that cycles water within the ocean and between the ocean and the land. But again, we have this really nice hydrologic or water cycle moving water constantly between the land, the ocean, the ground, and the atmosphere. Really sort of, I was going to say beautiful, but I don't know if I would describe the water cycle as beautiful, but a really elegant connection of our land, our ocean, our atmosphere all together around water as a resource. So let's talk a little bit more about groundwater, because groundwater is really important. It's not something we typically think about, but it really is a sort of important aspect of many organisms. Now, there are many ecosystems which we call groundwater dependent ecosystems. These actually support communities that require groundwater to meet some or sometimes all of their water needs. Now, for instance, we have underground water seeps like this, such as those in deserts, where underground water basically seeps up in pools, and organisms that live in these very, very dry areas heavily rely upon these seeps from groundwater. But there's also some really cool crustaceans. Now, the species is called Niphargus aqualex. Genus species names are always hard to pronounce, but they're called, these organisms are classically called stygobites because they live in underground water. They rely totally on underground water sources for food, for living. And the sort of the cool thing is with a lot of these species is they don't develop any pigments. So they're completely clear. You can see its full digestive system here, because it lives underwater in our groundwater. So pretty cool group of organisms. There's all sorts of, if you guys have never seen like Planet Earth with David Attenborough and those series, they do a whole great thing about groundwater dependent organisms, and they're really wild. They're all clear and they lack pigments, and it's a really cool group of organisms. But I'll move on because I'll just keep talking about these cool things because again, I think they're cool. Now, this leads us to lakes and ponds. Now, as we discussed, they're the most commonly available source of water for humans. And these are lakes and ponds, as well as streams and rivers and brooks and all the other things you can think about. All are what we call surface water ecosystems. Now, how does one of these forms? Well, the reality is they basically have to have a low-lying area, and water essentially collects in there. Typically speaking, you get a deep area forming via glaciation. So, for instance, the Great Lakes, where we store about 50% of all of our fresh water on the planet, formed during our last ice age, and monstrous glaciers basically came through and carved out these very, very large areas, very, very deep areas, giving us our 5 Great Lakes that, 5 Great Lakes that we know, and some of us love. But for those of you that don't know about the Great Lakes, some of the Great Lakes are immensely deep. So, for instance, Lake Superior is well over 1,000 feet deep at spots. So really, really deep areas. But again, glaciers, typically speaking, are carved these large indentations, leaving these places for water to accumulate over time, thus creating our lakes. Now, we can also see actually see some other interesting things, which we call oxbow lakes. Now, rivers, they flow typically in one direction, but as rivers age, they can form these little oxbows where essentially they erode a piece of the land and create a new flow. And as they sort of create this new flow, over time, they erode the land here, thus creating a small lake all on their own, or small pond, I should say. But again, most lakes form because of our glaciers, but again, we can also have some natural things like this. And then the final way you can actually get lakes is actually by impacts of asteroids and meteors and stuff like that, and volcanoes as well. So when asteroids hit, they create indentations. When they hit, if they create a big enough indentation, it can create a lake, right, if enough water falls in there. But also collapsed volcanoes can also fill with water, thus forming a lake. So kind of a cool thing. For instance, here we have Crater Lake in Oregon, which is actually one of the deepest lakes in the United States, which is kind of a cool thing. Now, lakes and ponds are places, as many of you probably know, they are vibrant ecosystems. And when they're vibrant ecosystems, partially because they're what we call lentic ecosystems, because they have relatively stable water, very, very stagnant water, allowing things to essentially form a really cool ecosystem at different depths. So we have what's called 2 different distinct zones forming here, where we have the littoral zone or the littoral zone, whatever you want to call it. Now, this is basically the part of land that's relatively shallow, but actually is relatively close to the edge of the pond, or lake or whatever we're talking about here. And this is the place basically where it's shallow enough where plants can settle in, including cattails and pond weeds and other things at the bottom, creating essentially this mini, you could also ultimately think of it like a forest ecosystem where you have, again, plants and all the things like that. And this brings with it a huge diversity of life, including fish and insects and crustaceans and all that sort of stuff. And after that sort of littoral zone, as you move out towards things get deeper and deeper and deeper, we form what's called the pelagic zone. The pelagic zone is also actually a name of place of the ocean. So the pelagic zone in an ocean is a very similar thing, just a very, very deep part of the ocean. But the pelagic zone is pretty interesting because it is pretty heavily what we would call, forgot the technical term. Crap. It's pretty heavily divided into two distinct areas, what we call the photic zone, i.e. where photosynthesis by plankton and algae can occur, and then the aphotic zone where there is no light and basically things settle in there to die. Aphotic just means the absence of light. Photic means the presence of light. So you have the photic zone with photosynthesis going on, supports insects, supports large fish. And then you have the aphotic zone, which doesn't support any photosynthesis, where things basically go to die and are consumed by bacteria and other things. So kind of a cool sort of stratification of lakes and oceans. I hope this, if you've never sort of thought about this or seen this before, the next time you go to a lake, you sort of see these things. Now, as I mentioned, lakes and ponds are pretty are static. They don't have a lot of movement to them. There's no like currents, but very, very large lakes, such as the Great Lakes, do have currents. So for instance, for those of you that have never been to any of the Great Lakes, for instance, when I was I went to Lake Michigan a couple of years ago, there's actually waves in Lake Michigan because of how big it is. So generally speaking, lakes are pretty static, but larger lakes can have some pretty interesting water movement to them. And then we have our lakes and our streams and rivers. Now, these are flowing water. They can flow very, very fast, very, very slow. But they are what we call lotic ecosystems, basically where they form differential habitats based upon how fast the river is flowing or the stream is flowing. Now, you might think all rivers flow relatively fast, but the reality is essentially the geology of rivers allows them to essentially create different habitats. So very, very fast rivers, i.e. those that are coming straight down from the mountain, don't really have a ton of life living in them, mostly just plankton and stuff like that. But as the gradient decreases, you start to get essentially slower things, allowing for more communities to come in, fish, plants, things like that. Eventually, lakes and rivers potentially flow or become a wetland, i.e. permanently wet areas of soil, including things like marshes, and they can be dominated by things like grasses and cattails. But they also invite large numbers of birds, beavers, things like that. And then eventually we get to sort of the what we would call an estuary. And estuaries are basically areas where they enter the ocean. Now, estuaries can dump into marshes. So you can see a salt marsh here, or they can also just dump directly into the ocean or potentially through a mangrove swamp, one of the two. But again, our rivers are sort of this dynamic thing. They change pretty heavily depending on how fast the water is flowing. Fast flowing water, not a lot of life. Slow flowing water, lots of life. So that's kind of our thing. Now, as I mentioned, our wetlands and estuaries are part of our river system, as we sort of see in this area here, as well as coastal wetlands as well. And these are essentially seasonally or permanently saturated with water. And they're actually they're actually my favorite ecosystem on the planet because you have this really sort of dynamic system where you have this permanently wet area, which allows for the settling of all sorts of cool organisms and things like that, and bring in all sorts of neat life and birds and all sorts of stuff like that. Then we have a category of wetlands, which we call estuaries. Now, these are where freshwater meets saltwater. Now, for those of you that are from New England, we typically call these salt marshes. So we have these really beautiful grassland ecosystems. that connect the land to the sea. They provide this really nice interface. And wetlands really do provide that interface typically between, stream and stream, stream and ocean, river and lake, something like that. They basically, estuaries and wetlands form this interface between these different parts. So those are sort of for all of our key wetland ecosystems out there. Now, let's talk about how humans factor into fresh water, because as I mentioned, we consume about 80 to 100 gallons of water a day. So if there's 300 million people in the United States, we're consuming about 100 gallons of water a piece a day. We're taking about 300 billion gallons of water every day from our water sources here in the United States. So it's a pretty substantial amount of water. So how do humans impact our water system? Right. So we can start to ask questions like, how did Flint, Michigan become contaminated? Right. How did their drinking water become contaminated? How do our groundwaters our water become contaminated with forever chemicals? How do humans factor into this? Well, the reality is, if we think about a situation like Flint, Michigan, where they're drawing water directly from the Flint River. The Flint River and Michigan as a whole is a pretty, at least formerly, a heavily industrialized area. So there's lots of nasty stuff in the waterways around Michigan. And the water from in Flint, Michigan is drawn directly from the Flint River, pulled into a water treatment plant that tries to disinfect the water from the river, as well as try to remove any toxic chemicals. And then from there, it's pumped through water. Now, the reality is, that pumping of water goes directly to people's houses and businesses, but let's take a peek at the pipes here. Now you can look at, we have these connector cables, which are lead soldered. So there is lead connecting copper to these pipes. So there is lead, sort of soldered onto these pipes. And water is not particularly a nice chemical. All the time. Now, it is essential, but water, as it sort of does its thing, can actually be slightly corrosive. So what's happening is they're drawing water from the Flint River that does have slight corrosive properties from that. And because it is slightly corrosive, it's damaging the pipes, touching the lead in these connectors, letting the lead get into the water, thus making it into the homes of average everyday people. So that's sort of one way we can see a failure of our water infrastructure system in Flint, Michigan. But there's lots of ways humans impact our water, not just by poisoning ourselves with our own infrastructure. Now, I'll just make mention of one thing. This has been going on for about, 5+ years at this point, and nothing has meaningfully been done for the folks in Flint, Michigan to fix this problem. It's about a $55 million problem to fix. And for those of you that know Flint, Michigan, it's one of the poorer areas of Michigan. And so not a lot of tax dollars coming into that area, unfortunately. So it is a problem that still exists to this day. It hasn't been fixed, and doesn't look like there's an end to this issue in Flint, Michigan, even within the next couple of years, unfortunately. So that's Flint, Michigan. But let's talk a little bit about how we draw upon water. Now, in the case of our friends in Flint, they're drawing directly from a river. But the reality is, as humans move across this country, as we move across the planet, we always have to find new sources of water. And advances in technology have allowed us to actually physically tap more and more into underground sources of water, these aquifers. So we can look at a map here of drawing from what we call the Agala. I'm not going to try to say this aquifer. Sorry. As you guys figured out by now, punctuation is not my strong suit. But it spans Nebraska, Colorado, Kansas, Oklahoma, Texas, New Mexico. So it spans and South Dakota, Wyoming as well. Pretty expansive area of the country, area-wise. Not a hugely populated area, but for those of you that know a little bit about the geography, you'll know that Denver's not too far from here. So there are some relatively large cities near here, but most of this area of the country is not very heavily populated. But one thing that this part of the country does pretty well is agriculture. And I'm sure you guys probably know Nebraska is big corn state. That's the corn huskers there, that their state university's mascot. So lots of uses for water, even though there's not a ton of people living here. Now, But you'll notice on this map where we have water level change, red is basically a change of net loss in the water capacity. There we go. And anything that is essentially blue is essentially a gain in water capacity. But what you'll notice in this aquifer, as we take and take and take from it, it's losing and losing its source amount of water found in it. Now, groundwater is typically what we would consider a renewable resource, i.e. it replenishes itself over time. But the replacement time can be relatively slow. So there's some aquifers that take well over 10,000 years to replenish themselves because of how slowly water moves through the underground. But the reality is this is a resource that does replenish itself, but it can only replenish itself so much. So for instance, if you have a bag of Skittles, if you take all the Skittles and dump them in your mouth in one go, well, that bag of Skittles is gone, right? But if you think about if I eat one Skittle every day for a couple weeks, well, those Skittles will last for an extended period of time. And so that's the same thing that's sort of going on here. The more and more and more you take, the faster you take it, the less likely our groundwater systems are to recharge themselves. Now, one of the other things that we're actually seeing as a result of lack of more and more taking of groundwater is actually the shrinkage of our rivers and wetlands. We're also seeing what we call salt pollution or saline intrusion. And now, sort of a weird thing, but as you take more and more from the groundwater, less of it's making it to the ocean. Also, less of it's making it to our rivers and lakes and stuff like that. But when less of it makes to the ocean, it actually allows more and more of the salty groundwater to penetrate into our fresh groundwater, thus making our fresh groundwater more salty, less able for us to use for things like that. And the other thing we're actually seeing is actually called subsidence, where you can actually see this really fun picture here, where this guy here has he has this little pole where at the top of the pole, that's where the essentially the height of this used to be. And you can see here at 2013, that's where the height is in 2013. And basically what's happening is this entire valley, because we're taking so much water from the groundwater, is causing the level of the surface to actually go down, which is kind of an amazing thing. 7 feet of essentially lowering of the land because you're taking so much water from the ground in essentially a 40-year period, which again, I think is absolutely crazy to think about. 7 feet, again, really, really crazy. So now that's our groundwater. We also disrupt our above ground water systems. Now, how do we do this? We've been doing this for a very, very long time. The Romans started doing it pretty heavily with their aqueducts, but we do divert our water in a number of ways with our impervious surfaces. Now, you might not think about your driveway or your roads or your rooftop as a way to change water, or parking lots for that matter. But the reality is hard surfaces don't allow water to seep in and sort of push water into different areas than it's not supposed to go. That changes the way water flows in our ecosystem. So if you have a heavily developed urban area, the way the water flows is not the way it's supposed to flow. It flows into pipes and things like that, and thus changing the hydrology or the way water moves in areas like that. But we also know that we've changed pretty heavily the way water flows by doing things like canals. Those of you that have ever been to the Cape, you know, you go over the Cape Cod Canal. We know the Cape Cod Canal was dug over a period of, 20 to 30 years, or no, about 10 years, to connect both sides of essentially to cut directly through Cape Cod. So we like to cut channels to divert water. We also like to build dams. So you guys probably know that the damming of the Colorado River produced Lake Powell. Also, we know that the what's the lake that shoot? Sorry, I'm drawing a blank here. There's one in China that's done the same thing. Can't remember what it's called, but we know that we can pretty heavily change the way water flows just by building our structures, whether it's for something good or maybe something not so good. It doesn't really matter. We do heavily change the way we go. But the other thing we change pretty dramatically when we change the way water flows is two things. The first is fish. Fish have their own sort of way they like to swim and their habitats that they like, but building the Hoover Dam or building a canal changes the way fish swim. Thus, it impacts migration of fish. But the other thing that doing this, putting hard structures, changes the flow of sediment. and changes the way we erode our sediments. And so one of the things we're actually seeing is the accumulation of sediments in different parts of our our coastal systems and our rivers and stuff like that, which again further changes the way our water flows. So kind of an interesting sort of change, not something you might not think of. Pretty commonly, but again, we do change pretty heavily the flow of our water. And again, canals are a pretty common thing. Now, man-made channels do impact our aquatic habitats. And so, for instance, we have this estuary habitat at the mouth of the Colorado River here, where it meets the Gulf of California. It's actually been reduced by more than half because of all the upstream diversions of water. I'm sure you guys probably have heard of the Mississippi River is at all-time lows because of increased changing drainage of water from the Mississippi River. Really sort of dramatic way we disrupt surface water. So we're dramatically taking lots and lots of water out of our systems, but we're also pretty dramatically changing the flow of water. But as we saw with Flint, Michigan, we don't really treat our water in a particularly awesome way, which leads us to water pollution. Now, we're going to talk about water later on. We're talking about waste and pollution and stuff like that later on in the semester as well. But I want to talk a little bit about some ways we pollute our water and how our waste products pollute our water systems. So we have two different types of sources where we have a point source. And so, for instance, we have this factory here, and it has a wastewater treatment plant, and it dumps pollution into our rivers or oceans or whatever. This is what we call a point source of pollution to our waterways. We know exactly where it's coming from. Now, this is in contrast to a non-point source. A non-point source of pollution to water, i.e. all the runoff from all the houses in a town. That would be a non-point source. So a point source, we know exactly where it's coming from. A non-point source, we don't have any idea quite so much where it's coming from. It's probably coming from multiple different avenues. Now, this breaks down a little bit more into three distinct types of pollution. The first is sediment pollution, and it's actually pretty dang common where we have large amounts of loose soil that are put into our waterways, which causes our waters to become turbid and reduce light penetration. We see this pretty heavily in the Charles River, for instance, where the Boston Harbor is pretty murky because of all the sediment pollution because of our activities along the Charles River. We also have chemical pollutions. Now, Flint, Michigan was a great case of that. We had lead poisoning, but it could be any number of polluting chemicals, including forever chemicals, plastic-based chemicals, heavy metals. Anything you can think of really falls into chemical pollution. And then we have biological pollution, which is typically speaking from our livestock, i.e. we have poop from cattle or poops from feedlots that run off into our systems as well. So clearly no shortage of places where we can pollute our water. That's for sure. Now we'll talk more about waste later on this semester. In particular, we'll focus pretty heavily on plastic as a waste. So don't think this is the end of us talking about water pollution. Now, let's talk about access to water because clearly it's not equal, right? We sort of started the class off by saying, I asked you guys to sort of think about, have you ever worried about your water? And the reality is access to water is not uniform. As I mentioned, about 1 billion people suffer from water scarcity on the planet, which is a lot, right? 3 times the population of the United States suffers from water scarcity in some way, shape, or form. And I'm sure you guys have probably seen pictures or videos like this of people in sub-Saharan Africa carrying water on old dilapidated containers simply because they don't have access to water or modern plumbing in their houses. Now, there are some regions of the world, including in Africa, including Mali and Niger, where more than half of the population actually lacks access to safe drinking water, which is pretty stark. And that's, some countries it's more than half, which is, again, it's a pretty stark contrast. And you can see sort of these pictures where people are walking hours and hours to obtain their fresh water. And it's sort of an amazing thing that you can have, this existing in Africa, but also the United States, where we're consuming hundreds of gallons of water on a weekly basis, where they sort of stand in stark contrast to one another. and sort of this idea of not having access to fresh water is what we call water security. And now the water insecurity, which leads us to talking about water security, i.e. ensuring reliable, safe access to affordable water. That's an important note. Some places have plenty of water, but it's been privatized in some shape or form, which makes it not affordable to the residents that are living there. So that's kind of another thing. But water security is a major goal of the United Nations, as well as many other international bodies as well. So it's kind of a stark thing again. Again, you can have great excess and great lacking of water, all existing within the same planet, within the same country, within the same region. It's kind of always an amazing thing. So let's talk about how water is used differently. So let's talk about this in the case of cow milk or almond milk, though if you ask dairy farmers, they would never want you to call it almond milk. It should be almond beverage, but I think that sounds weird. So I will always keep calling it almond milk, regardless of what any dairy farmer says, because almond beverage sounds, I don't know about you guys, it just sounds weird to me. Now, cow milk, I mean, I'm not a personal fan of milk in general, but cow milk is clearly an important part of American life, important part of people's average everyday diets. And it's not just true here, it's true across the planet, because milk is used to make awesome things, right? It's used to make cheese, yogurt, things like that. So milk is clearly an important part, but in the recent decades, we've actually seen a rise in milk alternatives, almond milk, soy milk, oat milk, things like that. Personally, myself, I like almond milk. I think it tastes really good. But let's talk about these two milks, or two beverages, or whatever you want to call them. And so we know that almond milk since 2010 has actually grown by more than 250%. I'm sure I've helped contribute to that. But the reality is we can actually look at how many gallons of water it takes to produce 1 glass of soy milk, 1 glass of almond milk, and 1 glass of regular milk. And we can see that 1 glass of soy milk does take about 9 gallons. So it's healthier, at least from a water standpoint, a better choice. About 23 gallons to produce 1 glass of almond milk, and about 30 gallons to produce 1 glass of regular milk. Certain other types of milk, such as oat milk, require maybe about 5 gallons of water. So some other milks do a little bit better. Others, as you can see, do a bit worse. I will say, though, regular milk is the most water intensive of all the milks. Obviously, I think chocolate milk is probably the most intense of all of them, because it takes both cows and chocolate together. So just as a note. And then we can think of things that require milk. Now we can think of yogurt. Just regular garden variety yogurt requires about 35 gallons of water, and about 1 Greek yogurt, which I would argue is the better of the 2 yogurts, takes about 90 gallons of water. So pretty heavily scaling up how much water is used between our milk. Now, almond milk requires about 490 gallons of water for each gallon of almond milk to produce. So if you drink a gallon of almond milk, try saying that 5 times fast, it takes about 500 gallons of water to make that. Now, the region of California actually has pretty heavily devoted its irrigation of almond orchard. And they're actually one of the largest producers of almonds in the world. California is the biggest producer for a lot of things in the world, just because California's got great soil, but they do produce a ton of almonds, not olives. Now, it's actually kind of interesting, because of all the irrigation for almonds and how popular almonds have become as both a drink and a snack, they're actually experiencing some of the greatest droughting conditions since 2011, which is pretty stark. Again, all just because producing more and more almond milk. Now, the important thing that sort of separates almond milk from regular milk is that almond milk is just straight water that goes to make the milk, right? You need milk to make the tree and to process the almonds. But when you think about why it requires so much water, it's just because the almond trees need so much water. So they're not really a very green tree in terms of water, as far as water is concerned. But you think about what was required for milk. Milk requires the cows need to be fed the milk, but you also need to introduce milk. Cows need to be fed the water, but they also need water in terms of producing milk at the end process. So it's kind of a double-edged sword for producing milk, just as a note. Now, clearly, agriculture uses a lot of water, and just to put that in perspective, agricultural irrigation uses about 70% of all water on the planet. 70% just to grow food and our dairy products and things like that. So it's just a massive amount of water going to our food industry. Industry uses about 20%, and the rest is about 10% of just residential use. So, which is kind of yeah, kind of a crazy, sort of a weird way to think about how water is used. Most of it's just food, right? A lot of it's used by industry. Very little of it actually goes directly into your mouth. Now, the reality is how you get your water differs. A lot of people drink water out of the faucet, but about 12.8 billion gallons of water is actually bottled and shipped around the world. So not only do you have this direct consumption from the tap, but you also have this massive bottled water market out there as well. So not just from your faucet. But because we drink so much water, both directly and indirectly, it's caused some pretty severe water shortages across the country. Now, for those of you that live in Massachusetts, you know that Massachusetts was basically in a drought pretty much perpetually for the past 5 years. And we actually just got out of our drought here in Massachusetts in the past couple of weeks because of all the massive amounts of rain we have. But that's Massachusetts. We're on the scale where you have darker reds are drought, with i.e. exceptional or extreme drought, and then yellows are basically slightly dry, with white being no drought at all. And you'll notice that a huge part of our country, in particular in the American Southwest, California, and the Pacific Northwest, have suffering some pretty severe droughts. And that's just not limited here. You're also seeing some pretty severe droughts down the tip of Florida, as well as in the Dakotas. But drought has really existed pretty much everywhere throughout this country at some way, shape, or form. Kind of a sad thing. And it's not just true here for the United States. Globally, we're seeing high amounts of drought across numerous nations as well. Now, for the first time in the history of California, actually, Governor Jerry Brown did order his residents to cut water use by 25% in 2015 because of how much drought they were experiencing. So it's kind of an amazing thing. And California, like Massachusetts, has been a perpetual drought as well. But interestingly, very, very high levels of precipitation did end California's drought in 2017, but they do have a massively growing population, a massive agricultural base. So their water shortages are actually back in full force now, which is kind of an unfortunate thing after getting out of it. Now, how can we potentially conserve water given this picture here? Because, I mean, clearly this picture is just of January 8th. This is just from January 8th, 2019. But again, every place in the country has experienced some form of drought. So how can we conserve water? And it's kind of a hard thing to do, right? If 70% of our water usage is in agriculture, how can we think about recycling water, right? How can we think about taking the waste products of our water to use other things? So one of the things people have suggested to do is actually build infrastructure to allow the treatment and recycling of residential water, not industrial water, but residential water, to essentially be used by our farmlands and things like that to help conserve water, i.e. letting less water go to waste. Really important part of keeping our water safe is trying to conserve it as much as you physically can. Now, water scarcity, because we're drawing so much water, is clearly a big issue. Now, historically, one of the best ways to provide constant water source is damming things. But damming things, as you guys probably know, has some unintended consequences by changing the local areas that they dam. But the reality is we do know about 25% of the population does experience some sort of water scarcity. And this is not just because of drier conditions, but it's also because of the privatization of water by either local municipalities or companies such as Nestle that essentially try to turn water as a profit. And to put this into further perspective, water was just starting as a commodity to be traded on the New York Stock Exchange in recent years. So water is clearly a valuable thing, and it is clearly something that is very short that people, again, will look to commoditize in some way, shape, or form. Now, one other ways that some countries have took to harvesting more water is some pretty cool harvesting of rainwater. So this is like a more of a industrial way to do it, but you could also think about like you have a rainwater barrel at your house. But other countries have adapted desalination, where you take water from the ocean, pull the salt out of it to create fresh water. But the reality is that's an extremely energy intensive process and not one that's really applicable on an industrial scale at this point in time, but will certainly become something that is necessary going forward. So the question we can ask is, if water scarcity is such a big problem and drought is a big problem, how do we keep freshwater clean? Now, the United States, about 90% of the population is served by a water system with no violations to, codes and stuff like that. Many communities do suffer from unsafe water supply, as we saw in Flint, Michigan, and globally, as we mentioned, about 2.5 billion people do lack access to sanitary wastewater systems. And so how do we essentially keep our freshwater clean? And there's a number of ways we have to do this. Now, we have this really interesting wastewater treatment plant idea here, where we have wastewater that arrives at a sewage treatment plant. It gets initial chemical treatments where you separate solids. Those solids are trucked away for a separate disposal facility. Then we have an increasing number of facilities where essentially the finer solids undergo much more further processing, can eventually be made into fertilizer. And then eventually the remaining liquid is actually treated into what we call bioreactors, where we use bacteria and enzymes to decompose and help clean the water. And then we treat them oftentimes with chlorine or ozone before we essentially let that water get out in there. Now, this is in an idealized way. Clearly, this doesn't happen everywhere. It really isn't, but it is actually a huge part of what we would call the Millennium Development Goal that was put forth by the UN. That it's trying to help ensure environmental sustainability on our water as a whole. Now, there's many technologies that come out from this, including the solar water cone, which is actually a pretty cool thing. If you've never heard of the solar water cone, I definitely recommend that you take a peek of it. It's a pretty cool little device, but basically uses the sun to desalinate water. So it's actually a pretty cool thing if you've never heard of it. Really simple invention, but really cool thing as a result of trying to keep freshwater clean. We're also seeing much more greener roofs, i.e. growing plants on top of roofs to help create less storm surge runoff from our roofs in our cities, thus keeping our water overall more clean. But the most important thing for keeping your water clean is regulation. Now, in the United States, we've enacted the Safe Water Drinking Act, as well as the Clean Water Act. Again, really successful pieces of legislation have kept millions of people from suffering ill and adverse side effects from polluted drinking water. Just as a note. Now, how does this enforced? Well, it's typically enforced through the EPA. The EPA monitors contaminants and does set maximum allowable levels from our drinking water. That does require some level of state enforcement. So certain states do a really good job. Massachusetts does a really great job. Other states, such as Michigan, do a pretty poor job. So it really does depend. The national resources are there, but they have to be enforced for them to actually be effective. And that's not always the best thing. Now, one important reservoir for fresh water is actually frozen water. As we mentioned, about 60% of all of our fresh water is trapped in glaciers and things of that matter. And as we know, since the 70s, climate change has causing us to lose massive amounts of glacial mass out there. And I'm sure you guys probably know all of our glaciers are pretty much found in the Arctic and Antarctic. They're essentially just permanently frozen areas of water. Now, these melt naturally, but also they have been melting not naturally, i.e. due to climate change, which we'll discuss later in the semester. And these ice sheets essentially come into the ocean and melt into the ocean, sometimes into rivers, but they do provide access to clean drinking water for those people that do, and individuals and animals, I should say, that do live in these areas. Not a ton, but they do provide some of those things. But the cryosphere, i.e. the amount of frozen water, has been slowly declining over time. So we can look at this map here of ice loss of meters of water equivalent, where we're seeing that over time since the 40s, we've seen a pretty dramatic loss of meters of ice loss over time. I.e. what we call our cryosphere. Now, along with the snow and the ice, we're also seeing a melting of the permafrost, which is water that's permanently frozen in soils. Just as a note, we'll talk about these ideas later in the semester when we discuss climate change, but I want to do foreshadow here. And then we're also seeing a loss of sea ice, as well as a change in what we'll call the albedo. And now we'll talk about the albedo later in the semester, but just know that the albedo is how reflective the Earth is. And that becomes important for our water cycle, because the more reflective the Earth is, the less evaporation there is, the more stable your surface water sources are. I'm actually going to skip this ice age part because it's not super important. You can take a peek at it if you're interested. But let's talk about the biggest source of water before it sort of get to the end of today's class, this part of today's class, and that is our oceans. Our oceans, remember, are 95% of all of the water on the planet, and the average depth of the ocean is about 2.3 miles, which scares the crap out of me. I don't know about you guys, but the ocean is a scary place, and knowing that they're that deep on average makes them even scarier. Now, massive amounts of water exist in the ocean. Lakes, rivers, streams all eventually make it to the ocean. But the ocean does contain 5.5 trillion tons of salt. That's a staggering amount of salt if you sort of think about how much salt that is. So that means the ocean's waters are undrinkable because they are very salty. Right? If you drink salt water, if you accumulate enough salt, you'll eventually go blind and eventually die. But the one things the oceans do really, really well is they actually influence our climate, i.e. the long-term patterns of weather we see at the regional as well as global scales. Now, as the ocean heats up due to the sun, it creates these little currents. And we'll talk about this in the next part of class as well, because we're going to talk about the air next class. But do know that as you heat up water, it causes mixing of water, which causes these water currents to form. Now, there's numerous water currents. I'm sure you guys have probably heard of this one over here. This would be the Gulf Stream. That brings hurricanes up here, right? So we had this happen earlier this summer where we had, what was the name of that hurricane that came up here? I don't know. It came up here from Florida, dumped a bunch of rain on us for a couple of days, and then went off up into the North Atlantic. But that's one type of oceanic current. And you can see we have multiple ones, including the North and South Atlantic Gyre, the Pacific Gyres, the Indian Gyre, and then actually the Antarctic as well as the Arctic currents. But how does this happen? Well, the reality is the water of the ocean heats up. As the water heats up, it causes it to move more, causes it to want to move up and down, thus causing these currents to form. As these currents form, it changes local climate. So for instance, you have this warm water coming across the Pacific, bringing cold water down into Southern California. This makes Southern California's climate very, very different than Upper California, or Northern California, I should say, where we have this essentially this large amount of hot water coming in, making the area much, much warmer. Now, why does this matter? Well, climate influences how much water evaporates, how much water loss there is, how much rain there is. So how the oceans are, how hot the oceans are influences how much evaporation, how much water is cycled on our planet. So the oceans are really, really important things overall. And the oceanic currents also affect these things as well. Just as a note. Now, there's a little thing you can take a peek on your own if you want to read a little bit about it. It's called the Coriolis effect. So the best way, and I like this example because the Coriolis effect is basically just a curvature of the currents on the planet. And so basically what it does, if you're you had a pitcher throwing a ball, the expected path, which should be straight, but the Coriolis effect bends things either to the left or basically to the left. Causing these gyres as well. So if you want to take a peek at the Coriolis first, definitely take a peek at it. But again, oceanic currents are important. They influence how water moves in the oceans, influences local climate, influences how much water evaporates, how much precipitation there is. But one thing that oceanic currents do is they do interact with what are called deep currents. Deep currents are just very, very deep currents in the ocean where there's cold water. And as it sort of goes things like this, it produces what we call a thermohaline conveyor, I should say. Basically just a large scale movement of hot water deep down, bringing up cold water overall, giving us this sort of situation we see here where warm water is coming from the equator, coming up along the coast of Massachusetts, dumping itself over the coast of Great Britain, which causes cold water to come up from below, bringing cold water along the coast of Morocco and things like that in Portugal, creating an overall cooler climate than you would expect given where they are. So it's kind of a cool thing. But again, these upwellings allow for changes in climate, changes in the way water hangs around in areas as well. So climates are, again, directly affecting our water, how much water there is, how scarce water is, and again, all through our oceans. The oceans are, I didn't dive too deep into it because there's a lot to talk about with how oceans affect water, but the sort of the key thing to take away from here is that our oceans and how warm the surface of the ocean is affects how much rain and how much water we have on our land. just that's the sort of the key takeaway from this part. And I'm actually going to just not talk about this today. We're going to talk about this with climate change. So we'll skip this slide, and we'll also skip this slide, and then we'll sort of wrap up by talking about the ocean. As you guys probably know, the ocean heavily supports life. There are millions of species, hundreds of billions of individuals in the ocean, and the ocean has some levels to it. So there's multiple levels to the ocean. So the intertidal zone is basically the beach, i.e. the place that gets covered in water part of the day. Then we move to the Nearctic zone, i.e. where corals and things like that are. It's very shallow water. And then we eventually move into the open ocean, or what we would call the oceanic zone, i.e. as we sort of go down into the continental crust, where we're seeing larger organisms, sharks, large fish, whales, things like that. And that's divided very much like or lakes were into the photic zone as well as the aphotic zone. And as you sort of go down, life changes. Eventually you get to the bottom of the ocean, which has really cool life, which we collectively call the benthic zone. We have all sorts of cool things like anglerfish and stuff like that. So the ocean, very much like lakes, does have some level of stratification to it. And each zone within the ocean supports different levels of biodiversity, and it is relatively unique. Though I will say the oceanic zone here, or what we would typically call the benthic zone, is pretty devoid of life, as you can really sort of see. Not a lot lives in the open ocean. The open ocean is more or less like a kind of like a giant desert. But the ocean, in particular, the ocean by land, supports some pretty important life. So about 25% of the planet gets its calories, most of its protein directly from the ocean. Now, where does that protein come from? Well, it comes from the intertidal zones. It comes from the Nearctic zones, the shallow zones of the ocean. So the parts of the ocean that are very close to land. Why is this the case? Well, sunlight is plentiful when you're close to land because it's not very deep. So it allows lots of algae, lots of things that feed on algae, shrimp, jellyfish, snails, and larger things, as well as essentially the settling of coral reefs. And as I'm sure you guys probably know, coral reefs are hugely important ecosystems for fish and things like that. So coastal ocean is really where it's at in terms of supporting life, both human as well as oceanic. Really sort of an amazing thing. But the reality is, with all the other freshwater that we've talked about, oceanic water is under threat. That's not it's not unsurprising. Now we talked about the deep water. We talked about oil spills in our previous class, one of our previous classes, where we talked about oil spills impacting the Gulf of Mexico. That's one way we impact the ocean. We also know that garbage and plastic pollution. So I'm sure you guys probably heard of the Great Pacific Garbage Patch, where there's this massive pile of garbage in the Pacific Ocean. We'll talk more about this problem later in the semester when we talk about plastics. There's a huge problem of agricultural runoff as well, which we'll talk about when we talk about food. We've already talked a little bit about overfishing, where we talked about overconsumption of individuals and resources from the ocean. A topic we'll talk about when we talk about climate change is ocean acidification, i.e. lowering of the ocean's pH due to climate change. So we'll talk about all these in depth, but just a little foreshadowing of the ways we directly impact the ocean. So this leads us to our final slide. What can you do? And this one is more or less your patterns. Now, the reality is you can sort of can get an idea of how much water you're using based upon your food choices. That's sort of the best way to sort of impact how much water you specifically use. Eating less meat, eating less water intensive agricultural products, things like that. And there's some other things here that you could take a peek at, certainly to get an idea of how you can improve your water usages and things like that. So it's kind of a well, not totally on you. It is something you can directly impact by lessening the amount of water. If you ever want to, just as a future thing, if you ever want to buy a house, using grasses and plants that are a little bit more water friendly, not using things like Bermuda grass, using much more drought tolerant grasses is kind of the way to go as well. So this is the one you can make a meaningful difference of, unlike some of the other stuff where, it's really the large corporations that are doing a substantial amount of polluting or climate change or whatever we're going to talk about. So that's part one of today's class. Would you guys like a 15-minute break or 10-minute break or so, or should we keep going? Because we're gonna talk about air next. So moving out of the water and up into the air. Do you guys have any preference? Yep. All right. So we'll take a 10-minute break. So let me nope, I don't want to stop recording. All right, we'll pause to resume this class. So part two might seem a little disconnected, but from the first part, but as we sort of touched upon a little bit, they are pretty directly connected, and this is going to be air. Remember, a huge amount of water goes up into the atmosphere every day, and that's really thinking about the air. So let's dive into the air. I've been on a quote kick lately. So this quote from Lucretius in 50 BCE, he said, air, I should explain, becomes wind when it is agitated. And I just kind of like that quote. I thought it was funny. So let's talk about it. Air obviously is really important. You breathe it in and stuff like that. But remember, like the vibration of air allows you to speak, right? Allows you to hear and things like that. So never fear. Air is always a part of your everyday life. But let's talk about air. Air is basically everything around you. Air is, as you can see from this picture, where we have this Pennsylvania, big coal town of Donora, where they have huge amounts of air pollution. So humans clearly are not kind to the air, not kind to the water. You'll see, we're not kind to biodiversity. We're not kind to anything. Now, what do we put in the air? Well, lots and lots of different things. We put what's called carbon monoxide. You guys probably heard that one before. We put carbon dioxide. We put particulate matter, or PM, into the atmosphere, just like tiny bits and pieces of things in the atmosphere. Put nitrogen into the atmosphere. We put every number of things, anything you can think of. We put it into our atmosphere, which extends collectively about 62 miles from the Earth's surface. It basically just hugs our planet. So if you could somehow get into a car and drive vertically, you could exit the Earth's atmosphere in about 1 hour if you're going 60 miles an hour. So it's kind of an amazing thing, but clearly the air is an important aspect of biology. It's clearly an important aspect of sustainability and environmental science as well. So let's dive in. Let's talk about this air. Now, what are the gases found in our atmosphere? It's actually kind of a nice place to be a scientist in, because there's a very limited amount of gases found in the atmosphere. There's a limited amount of chemistry that occurs in the atmosphere. And as you can see from this pie chart that looks like Pac-Man, we have about 78% of the atmosphere is composed of nitrogen, N2 gas. It's basically biologically inert, basically does nothing, just kind of hangs around. 20% of that atmosphere is from oxygen, or O2. This is the stuff you breathe. This is the stuff that plants produce. And then we have smaller amounts of a couple other things, including carbon dioxide. That's what you exhale. Everything that dies produces CO2. We have other inert gases, mostly argon, about 0.96%. And then we have water vapor, i.e. just gaseous water, which we sort of touched upon last part of class, comprising about 1%. And this is collectively our atmosphere. Now, our atmosphere and the air around you is not static. Air moves. So when something feels very, very warm, it's just lots of movement of the air. That's all really temperature is. Kind of an amazing thing. It's just how fast the molecules of air are moving. The faster the molecules of air are moving, the warmer it is. Kind of a weird thing to think about, but that's what temperature of our air really is. But our atmosphere is always constantly in motion. They bounce around, they collide, and gas always fills whatever space or volume is available. Just the way it is. Now, a particular aspect about our atmosphere is what we call pressure. And simply pressure, as you guys probably know, simply the amount of force applied in a per unit area. So if you think about, like, if you take your hand and you apply pressure to the table, you're applying X amount of pressure over an X amount of area of your hand. Now, conversely, if you take your finger, your pointer finger, your middle finger, and you apply the same force to the table, you're applying the same force, but you're applying it over a much smaller area, i.e. the area of your finger relative to the area of your hand. So the pressure, is higher when you're pressing down with just your finger than if you're pressing down with just your whole hand. Kind of a weird thing to think about, but I think another way to sort of think about this is actually that this little girl here, she's blowing up an air balloon. She's blowing up a balloon with air from her lungs. Now, as this balloon expands and expands and expands, you increase a couple different things. You're increasing essentially the pressure inside the balloon. The pressure of the balloon is pushing the balloon outwards, thus getting bigger. But she's also increasing the temperature of the air because of her body heat. As you guys probably know, as you talk, your breath is warm, right? So she's increasing both the pressure inside and the temperature inside, causing the balloon to expand. It's kind of a cool thing about air. Now, it's a really interesting thing. When we think about air pressure, it simply refers to essentially the amount of air molecules, so the nitrogen and the oxygen, basically hanging out on top of you. It's kind of a weird thing to think about. But let's look at what we look at here. We have elevation here in kilometers on the y-axis, and the pressure here in millibars on the x-axis. But you'll notice that the higher up you go, the lower the pressure, and the farther down you go, the higher the pressure. Now, why is that? Well, if we look at this little white piece here, pressure, as in terms of air pressure, is simply how many air molecules you have hanging out above you. So the higher you go, the less air molecules there are, the less air pressure there is. So for those of you that are like me, when you hop inside of a plane, your ears pop, right, when you get up to 33,000 feet. Why is that? Well, there's a change in air pressure. There's less pressure above than there is down there, leading to a change in pressure of your ears, causing your ears to pop. I know it stinks, but that's just what it is. And we can think about, by the time we get up to about 31 kilometers, about 99% of air is below 31 kilometers. But the reality is most of the air molecules in our atmosphere exist below about 5 to 6 kilometers. And again, most of the air pressure that we feel in the atmosphere, again, is below that 5 to 6. Is highest at ground level, because again, less air, higher you go up, the less air above you, the less pressure. It's kind of a cool thing. Also kind of a really weird thing to think about when you think about, I feel pressure from the atmosphere because of all the air molecules hanging down on me. It's, again, kind of a weird thing. Now, the Earth's atmosphere, again, extends about 60 miles upwards, or close to 100 kilometers if you're not on the imperial thing. We have a couple different layers of the Earth's atmosphere. The highest point is what we call the thermosphere. This is where satellites hang out, as well as the International Space Station. That's sort of the highest layer, and it's sort of an interesting thing. It's a bit warmer than a lot of the layers below it because of pretty high solar radiation, i.e. radiation from the sun, just the heat of the sun. We move down then to the mesosphere. Now, the mesosphere extends from about 50 to 85 kilometers up. Below that is the stratosphere, and this is basically where the highest of our planes. So, for instance, like Air Force One flies in the stratosphere, pretty high up. Weather balloons hang around in the stratosphere as well. But there's a really important layer of the stratosphere, and we'll talk about this today. We'll talk about it during climate change as well. This is called the ozone layer. Really, really important layer. We'll talk about it in just a moment. Don't forget about the ozone layer. Super duper important thing. And then we have a couple clouds. So for instance, our polar stratospheric clouds do exist in the stratosphere as well. And then finally, we get down to the troposphere, and this is basically the first 10 miles or so of our atmosphere. This is where we live. This is where Mount Everest is, so the tallest piece of land on this entire planet. But the reality is we have this pretty dramatic difference in not only pressure, but what can occur there. All the weather that we talked about last part of this class, the rain, the snow, stuff like that, all occurs within the troposphere. So the troposphere is where it's at, 5 to 10 miles thick. That's sort of where all the good stuff happens. And you'll notice that the temperature is pretty dramatic. It's warmer down here. As you go up, it gets colder, and then it kind of gets warmer, colder, and then it stays pretty cold out near space. So temperature changes pretty dramatically as well. Kind of an important thing, not so much what the layers do, but just to know there is stratification in the Earth's atmosphere. And then as you go up, there's less and less gas in the atmosphere as well. So just as a note. So let's talk about weather. And when we're talking about weather, it's all occurring in our troposphere. That's where pretty much all the weather occurs. Now weather, and we'll talk about this when we talk about climate. But just to sort of let you know, because we're going to talk about weather a bit, weather is simply the short-term variations of temperature, pressure, moisture, and wind conditions in a specific place at a specific time. That's our weather. So right now it's 70 degrees out. It's humid as heck here in Massachusetts. That is the weather here in Massachusetts. But if we talk about the climate, if I say that, on average, this is the temperature on this day over a 10-year period, that's the climate. Climate is long-term changes. So if you ever hear, the climate change isn't real because it was cold in the middle of the summer, well, that's just simply weather, right? Climate change is long-term changes, whereas weather is just, it's cold today, it's hot today, it's humid today. So just as a note. Now, I like this quote from Mark Twain about the sort of difference between the weather and the climate. Mark Twain's obviously a really awesome guy, but he has lots of cool things to say about science as just a regular garden variety writer. Well, not a garden variety, but just a regular old writer. And Mark Twain says, climate is what you expect, weather is what you get. So weather is the conditions of that day in Boston. Climate is what is the long-term trajectories of weather in Boston. So let's talk about temperature, because temperature is important. Now, temperature, you guys know, is it hot or cold, right? And you measure a temperature with some sort of thermometer. Now, how is the planet warmed? It's a really nice one-word answer, and it's simply sun. That's really it. It's my favorite question to ask people, because people think, oh, how is the planet warm? It's this complex answer. And the reality is just a one-word answer, and it's simply sun, or the sun, if you want a two-word answer. So the Earth is warmed by our sun. The sunlight, the radiation given off the sun takes about 8 minutes to get to Earth. It travels 93 million miles at the speed of light to get to our planet. And the cool thing about our planet is it's not vertically straight. Now, this picture depicts it as being vertically straight. It's not. It's on a slight axis. It's on a tilt that we'll talk about in the climate change lecture. But because it's on a tilt and because the Earth is spherical and not flat, just going to put that out there. The Earth is spherical, not flat. The amount of solar radiation that each part of the planet receives differs depending on its latitude. Now, as you guys probably know, the equator is pretty hot, right? The equator, the tropics, Central South America, all these places are pretty dang hot. Why is that? Well, it's warm because these places in the tropics get direct sunlight. And the sunlight is much more concentrated at essentially the equator of the planet. Again, much more consistent, much longer, and much more concentrated sun, making the equator much warmer. At higher latitudes, they get less direct sunlight, leading to colder areas. So if you ever wondered why it's cold here in Massachusetts and it's hot as heck in, say, Guatemala, it's because of how much direct sunlight we get versus how much direct sunlight they get. It's kind of a cool thing. And you can really see that here with the flashlight, right? At an angle of 50 degrees, the light spreads out pretty heavily. At a direct 90-degree angle, it's a very intense beam. And that's what we see here on the Earth. When you have this angle here, it causes the light to spread out, less intense, colder areas. So every now and then, this will pop up in trivia. Just as a note, it pops up every now and then when I've done trivia. So it's a good little trivia thing as to why the Earth has different climatic regions like this, the sun and the angle of the Earth. So it's kind of a cool thing. Excuse me. So let's talk about some unexpected consequences of severe weather. Now, we'll talk about this in the lens of the Sequoia National Forest. One of the places I've always wanted to go, but I have never been able to go. And I really want to go because as I'm sure you guys probably know, sequoias are the largest single living organism on the planet that's not a fungus, or not a fungus. They're just these absolute monstrous trees. But we can see some unexpected consequences of severe weather because in the Sequoia National Forest in recent years, because of some pretty extreme weather, they have some pretty strong droughts that's led to the loss of some of these massive and actually ancient trees. And once they get stressed like this due to water, again, i.e. Severe weather, they succumb to disease in insects. So biology is directly affected by our friend, the atmosphere, our friend weather. So just want to make note of that. And I think the sequoias is a great example of that. Now, this leads us to water vapor. Now, water vapor is just simply the water in the air, right? Water exists in the air as a couple different things, precipitation, humidity, as well as cloud cover. And that's how essentially those three things reflect how much water vapor is in our air, i.e. gaseous water. Now, humidity, which it's really hot, really humid in Massachusetts right now, is simply a reflection of the amount of water in a given volume of air. And the amount of humidity in the air actually can affect how much evaporation occurs. So if the air is very, very humid, not a lot of evaporation occurs. So it's kind of an interesting thing. But humidity, it's kind of an interesting thing. If you think about it as like a blanket, high humidity is like having a nice thick blanket on, whereas low humidity is kind of like having like I don't know, like the sheet of your bed, right? So it's kind of like water is a really good insulator. Air is a really good insulator. In particular, air that is air. It's a really great insulator. So you kind of think of humidity as kind of like a blanket. Now, there is another aspect of humidity, which we call the relative humidity. And this is where the amount of water in the air as a percentage of the maximum amount of water that the air can hold at a given temperature. So if you ever hear relative humidity, that's what relative humidity refers to. I think you really only see this in like weather reports and stuff like that, not common in a scientific sense. And then finally, just to sort of show you how you contribute to this. Obviously, you live on the planet and the water is evaporating around you. But if you think about how sweat works, right? We can think about our friend here, Roger Federer, arguably one of the greatest tennis players of all time, or maybe I don't know, it depends on who you ask. People that really like tennis probably have differing opinions than I do, but arguably one of the greatest tennis players of all time. Roger Federer here is sweating. Now, why do you sweat? Well, you produce all this sweat. That's water. It evaporates from your body, takes heat away from you. Now, Roger Federer here in 2000, the U.S. Open in 2018, he actually was sort of has a really great quote here talking about how we actually experience humidity. And Federer said, just one of those nights where I guess I just felt like I couldn't get air. There was no circulation at all. Yeah, it's uncomfortable. Clearly just kept on sweating more and more and more and more as the match goes on, and you lose energy as it goes by. And that really sort of gets at humidity, right? It sort of feels like a blanket on you, right? Feel like you're sort of trapped in this like cocoon of hot air, making it feel much hotter than it normally is. So that's humidity. Hate it or love it. I particularly hate humidity, even though I'm from New England. I hate it. Sucks. Though it's certainly not as bad as humidity down in like Florida. But again, humidity kind of stinks. Now, let's get to another atmospheric phenomenon, which we call barometric pressure. Now, you guys probably have seen the barometric pressure before. We'll talk about high pressure systems, low pressure systems. They're just simply referring to the barometric pressure, which is simply a measure of the pressure exerted by the Earth's atmosphere at any given point. Now, what does that look like? Well, this figure actually does a pretty good job of sort of telling us what's going on. Now, when we have low pressure, the air spirals upward in counterclockwise at low levels, pulling warm air, drawing more warm air in and pulling it upwards as well. Now, when we have a very high pressure system, it allows air to flow down, bringing cold air down with it. So I'm sure you guys have probably seen maps like this. You probably never put too much thought into what this all means, but we sort of have these high pressure areas here, again, pulling cold air down, lower pressure areas pulling hot air in, and they sort of have these cold fronts where you have these currents of air, these fronts of pressure moving throughout the country, giving us different things. So you can see we have this cold front, but it has areas of low pressure as well. And you sort of see it here, right? You have this warm front, but areas of high pressure going on there as well, and areas of low pressure. But you also have these areas where you have direction of front, where is it going, right? Our high pressure pulls things down, our low pressure pulls things up. Now, what causes this? Again, you've probably all seen this before, but really what's going on here, temperature and the pressure can cause pretty stark changes in our air masses. Remember, there's a bunch of air sitting on top of us. And these air, and you got to think about it as being this massive amounts of air, kilometers in thick. And these air pockets have relatively high amounts of humidity. And so if we can cause changes in temperature to change how much pressure, we change how much airflow goes on, changing how warm air is rising, how cold air is falling, changing the local temperature, as well as the local weather in those areas. Now we have high pressure systems. They're simply systems of cooling air that's becoming denser and heavier, which sink to form an area of high pressure and are usually associated with clear, dry conditions. So if you want a good day, you want a high pressure system. But sort of the opposite of that is our low pressure systems, and they're air where warm rising air cools and expands into higher and colder altitudes, which typically causes water vapor in the air masses to condense into clouds, eventually leading to precipitation. Now, we could look at an example like this where we have air pressure. We have low pressure here in white and green, moving into medium pressure in yellow, and very high air pressure here in reds and oranges. And we have this high pressure system. It's typically diverting Pacific storms around California. So you can sort of see this high pressure system, which we know is associated with a good sort of clean days, very, very high air pressure here, pushing this essentially this front, I say, away from California, at least Northern California. The Pacific Northwest, allowing air to essentially all this precipitation in this low air pressure here to essentially cause rain in places elsewhere besides California. So barometric pressure and these high pressure, low pressure systems really come together to essentially affect local weather conditions as well. And they are pretty dynamic. They change on relatively short timescales, a few hours, a few days, things like that. So that's pressure. Now, wind is an important part of air. If you have your air conditioning on, you have a fan on, it's producing wind, right, to cool you down. So wind is simply the air in motion as it flows from an area of high pressure to an area of low pressure. So you can think about it sort of like a whoopee cushion, right? A whoopee cushion is high pressure. As you push on the whoopee cushion, it expels air out of the whoopee cushion, making that awesome fart sound. But again, putting an air or wind current going forward. Kind of a cool thing. And obviously with the best analogy possible with a whoopee cushion. So let's talk about some of these really interesting fronts. So we have a cold front and a warm front, and you guys probably heard these terms at some point. Now, a cold air mass replacing a warm air mass is what we call a cold front. And then the opposite of that, a warm air mass replacing a cold air mass is called a warm front. So we can think about what's going on here. We have a warmer ground and cooler ground. Now, essentially causes air currents to flow from these areas coming up, essentially pulling the air upwards in a convective current, allowing essentially areas to have precipitation occur. Then we have a frontal system where we have warmer air gets pushed upwards under cooler air, causing essentially, again, clouds to form and precipitation to occur. Then we can have the lake effect. Now, the lake effect is pretty cool. For those of you that have ever been to upstate New York, or maybe you've been to areas of Michigan or Wisconsin or Minnesota that are along one of the Great Lakes, the lake effect is a big deal. But the idea is you have cooler air essentially comes in, gets pushed up by the warmer water from the lakes, because lakes stay relatively warm relative to the land around them during winter, which causes relatively large snow clouds to form, causing very large precipitation events to occur alongside the lakes. So for instance, my sister, she used to live up in Rochester, New York, right over by Lake, is it Ontario or Erie? Never can remember. And she used to get massive snowstorms up there, again, because of the lake effect. And then we have some other cool effects here, including the orographic effect, which is the effect of mountains on lakes and things like that. So again, we have winds coming together to form all these different fronts, which can lead to different weather events, as well as different climatic events as well. Lakes have a very different climate than the surrounding areas as well. So, but the reality is all these things are basically causing these changes in barometric pressure, which lead to pulling of air from different places, leading to large sort of storms. Now, one of the cool things we can actually see occur because of changes in our air pressure and things of that nature. I'm sorry, our wind. On air pressure here, on wind, is actually large storms, typhoons, hurricanes, things like that. Now, we talked about the lake effect, but continental land masses also affect our weather conditions. Now, the interior regions of a continent receive, on average, less precipitation than coastal regions because they are farther from the ocean. So it's drier in Kansas than it is here in Massachusetts. And as we mentioned, the Great Lakes can also produce some pretty serious effects. Now, one of the cool things we also see is that the topography, i.e., the up and down, the mountain, how mountainous things also influence how much rain and things like that. So when there are mountains involved, it's pretty dramatically affects rainfall. So for instance, the Adirondack Mountains in California are a great example of this. It's dry on the California side. It's pretty wet on the Nevada side. So again, have this mountains directly affecting local weather. It's kind of a pretty cool thing. So that's our weather, how it's influenced by the atmosphere. Now, how does the atmosphere move around? Well, the reality is it's just air currents. Very much like there's oceanic currents, there is air currents. Now, there's regular patterns of global air circulation. I'll show you a map of those in just a moment. But these patterns of atmospheric pressure and what we call the prevailing winds continue to circulate in the atmosphere, which can essentially pick up and transport things all over the planet, such as dust and soot and ash and pollution and radioactive pollution, whatever you think it is. And you can really see that pretty heavily here. We have a forest fire here. I don't actually know where this one is because it's just a picture I grabbed from the internet. Thought it was a pretty good one, but we can see this forest fire burning here. It's being picked up by the winds, being carried over. And just to give you an example of this, a couple of years ago, during those very large California fires, well, they've had large fires every year, but during the 2016 fires, I was in Colorado for a conference, and because of the air currents between Colorado and California, I could actually see the smoke from the fires all the way in Colorado because the air currents were carrying the fire smoke from California all the way to Colorado. It's kind of a cool thing. Well, it was a scary thing because obviously California was on fire, but it was a pretty cool thing to sort of see the air currents at work. Now, as we mentioned, the equatorial regions, you're thinking about the great jungles of the world, they receive some, someone's got their mic on. If you could just, thank you. The equatorial regions receive much higher direct sunlight. Think of the Amazon jungle and things like that. Now, more sunlight you get, this leads to more evaporation. Now, remember, evaporation is just when water goes from a liquid form into a gaseous form, rising into the air, going into the atmosphere, eventually falling as precipitation. Now, this creates a large body of warm and humid air at the equator. This is what we call the equatorial low pressure belts. And this actually supplies a pretty abundant precipitation to the tropical forests at equatorial zones. Then as the warm air rises, goes higher into the atmosphere, it starts to cool down and then descends and increases the atmospheric pressure, creating subtropical high pressure belts. So let's physically look at this. It's actually a pretty cool thing. So we have the equator here getting direct sunlight where we have low pressure zones here, lots and lots of evaporation coming up here, comes up, cools down, creates this lots of rain in what we call the subtropical high pressure belt because the pressure is high. And we have this nice little current coming. Cool, warm, the air comes up, cools, falls, warms up, and sort of forms this nice little cycle. Now, these little cycles are what we call Ferrel cells, and they occur at 30-degree latitudes. So they occur between 0 and 30 and between 30. Oops, I'm sorry about that, and 30 and 60. So there's this really cool phenomenon where you get really, really wet tropics and really, really wet subtropical regions. But then you have this really narrow band right here at 30 degrees north, 60 degrees north, 30 degrees south, and then again at 60 degrees south. It's kind of a cool thing where we call, there's a really sort of stark thing that occurs here. Does anybody know, or does anyone want to take a guess what occurs at these 30 and 60 degrees, 30 and 60 degree latitude marks? And sort of the best way to think about it is what occurs about right here in the United States. Does anybody know? Arizona is there. Or maybe you know better, the geography of South America. What occurs right about here? NASA likes to test stuff there. Well, think about it this way. Lots of water here drops on here. Lots of water here drops right here. But they have this little area here where there's not a lot of water. And so what we end up getting is actually deserts. So, yep, super hot deserts. Good guess. Fantastic guess. Yep, super hot deserts. Yeah, at 30, 60, and 30 and 60, we have the formation of deserts. Why? Well, again, you have this region where we have warm air coming up, it cools down and then falls. But then you have this sort of these pockets in between these little cells where you don't get any meaningful amounts of rain. Very, very little falls onto these arid regions, creating deserts. It's kind of a cool thing, right? They're this really cool little cells. They little Hadley cells forming, causing rain to be super heavy here, but basically very, very dry here. And again, really cool patterns of atmospheric pressure and the winds. And this, again, this occurs not just like here, it occurs everywhere across the planet. It's kind of a really wild thing about how our air patterns really influence our local weather, as well as just the formation of ecosystems, right? A desert is an ecosystem, and it will only form at 30 degrees or 60 degrees. Kind of I don't know, I think it's a really cool thing. Global patterns. Now, we can look at some pretty cool things. Now, because of the Coriolis effects, which we didn't really talk too much, but remember, it's just the curvature of water, essentially in this way, right? Curving this way and this way on the southern hemisphere, and as well as the Hadley effects. The sort of the way things move, it's not completely circular, right? I mean, completely linear, right? Things aren't moving perfectly linear. They're not moving linear here. They're not moving linear anywhere. Because the Earth is a sphere, things are curved. And so because things are curved, we actually get these really interesting air currents that essentially form essentially all over the place. So we can look at some examples of this where we have essentially one of the sort of the most famous winds was the northeasterly trade winds, where you would come down from Europe and essentially sail along this way to get down to Central and South America, as well as North America. Why? Because if you're going on a boat, well, you need the winds to push you down, at least formally. And so they would rely on these trade winds coming down from Europe, pushing them across the Atlantic into Central and South America, and eventually North America. And so we have all these different air currents. There's currents that occur directly across the equator. They have the southeasterly trade winds. There's essentially these little gyres that form. But the one that you're probably most familiar with is actually probably the jet stream. So we can see this polar front here, which is what we also call the jet stream. You guys have probably heard weathermen talk about this quite a bit. Now these form at altitudes about 6 miles above Earth's surface. Near the top of the troposphere, but basically they basically carry air currents that carry wind essentially across large spaces of land. In this case, carrying winds all the way across North America into Europe and across the planet. So, kind of really fascinating look at differential air currents across our planet. Now, because our air currents really connect our planet via the atmosphere, we transport lots and lots of things here, including dust. Now, there's some really wild things. And so we have a pretty cool example here where we have the Colorado Plateau in the Mojave Desert. Now, soot that's blown from the Mojave Desert is transported to two places. The first is it's transported here from the desert all the way across California into the ocean. That's one way it can go. And the other way it can go is actually across the entire state of New Mexico, traveling all the way to what are called the Pinon juniper forest of the Colorado Plateau, which is this region here. So again, air currents connect distantly and potentially unrelated ecosystems. And it's kind of a cool thing that you might not think of, like, oh, it's desert dust, but the desert dust is rich in all sorts of nutrients that helps allow these forests that we see here to actually physically grow. I know this doesn't look like it's a particularly vibrant ecosystem. This one does, this one not so much. But again, the dirt has lots of good stuff in here that helps this ecosystem function better. We see the same thing in Africa. The great winds that come off the Sahara Desert come all the way across the Atlantic and land in the southeastern United States. They land in Mexico, and they land pretty heavily in the Gulf of Mexico, providing lots of cool nutrients to the Gulf of Mexico. It's kind of a cool thing. The other thing we can see is that soot from forest fires in North America we can actually see them in Greenland, where we can actually see the soot blackened ice in Greenland because of large fires in North America. We also know that volcanoes can also release particles into the air, which can in turn cause them to collect water, causing rain, thunder, and stuff like that. But you can also see volcanic ash spread out all across the globe. If you guys are up to date on your movies, there was a recent movie with Chris Pratt on Amazon, The Tomorrow War, that recently came out, and they actually talked about this idea of volcanic ash being as a way to figure out where aliens came from. I know that sounds lame, but that was the end of the movie. So just as a note, I hope I didn't spoil anything. But I thought it was a good analogy to sort of show you how the atmosphere really helps move things around in particular particulate matter. So it's kind of a cool thing. Now, how does the atmosphere become polluted? We sort of already discussed this a bit. It's mostly by, I mean, there's lots of natural things, but when we're thinking about pollution, we're thinking about the addition of atmosphere things that typically aren't generally there, or things that humans potentially put there. Now, what are some things you can see inside the atmosphere? Well, natural things include volcanic ash and pollen. The atmosphere is chock full of pollen, but also things like soot from fires, as well as salt from the ocean, as well as particulate from the combustion of fossil fuels. All those things are in the air, and they are teeny tiny. So you can sort of see the scale here. 1 micron is, just to put this in perspective, 1 micron is 1/1,000,000th of a meter. So it's a really, really tiny, it's microscopic. To put this in perspective, 1 micron is about the size of your average bacteria. And 500 microns, 0.5 microns or 500 nanometers is about double the size of, say, the coronavirus. So just to put the size into perspective here, it's kind of just wanted to make that known. Now, all these things, whether they're human-induced or just natural things, are what we collectively call air pollution. Now, we might not think of pollen or salt as pollution, but they kind of really are. Now, there are some different types of pollutions out there. The first is a primary pollutant. Now, this is simply something that is harmful directly in its emitted form. So, for instance, pollen is a great example of this. It is directly harmful in its emitted form. You could just ask me. I get allergies all day, 24/7, 365, because it is a primary pollutant and pollen stinks. Now, a common primary pollutant we get exposed to quite frequently is actually carbon monoxide, which is actually due to the incomplete combustion of fossil fuels. And so we get lots of carbon monoxide produced when we burn fossil fuels. Another example from this is actually some pesticides, benzene, which is a byproduct of gasoline, as well as asbestos in construction activities, all come together to form primary pollutants, things that are directly harmful to you. And this figure does a really nice job of showing you that it's really, really small. Really, really small stuff has a great impact as a pollutant. And then we have one primary aspect of our primary pollutants, which is particulate matter, or PM, which is basically any form of particulate air pollution that is less than 10 microns in size. And stuff we can breathe in readily, hangs around in the air. That's what particulate matter is. Particulate matter will become important when we talk about climate change, because it's a really big byproduct of lots of combustion of fossil fuels. And there's many other stuff that you might not think about as being primary air pollutants, including toxic heavy metals, lead, lead, mercury, arsenic, things that can readily travel through the air. And so if you guys have ever gone to the gas station and wonder why it says unleaded gasoline, it was actually kind of an important thing. So when we used to harvest petroleum, it used to be chock full of lead, and we combust that lead, producing lead pollutants in the air. Now, in 1978 and 1986, we banned both lead paint and leaded gasoline. So in 1986, we no longer had gasoline that was leaded, had to be unleaded. Why did we do that? Well, lead, when it was combusted in your car, would essentially produce an air pollution that was very, very toxic. And so we had this environmental regulatory action to get rid of air pollution. It's kind of a cool thing. Good aspect of actually regulating the fossil fuel industry, which is not something we do a particularly great job of on average everyday basis. So that's our primary pollutants. Then we have our secondary pollutants. Now, these are the product of reactions that occur in the atmosphere. Now, for instance, a great example of this is actually smog, which is it's a joining of smoke. Oh my goodness. Sorry, I just completely had a brain fart about what smog is. Oh my goodness. Shoot. Anyways, I'm going to move on because I can't remember what smog. I'm so stupid. Smoke and something else. Crap. Anyways, it's a bunch of smog itself is a mixture of secondary pollutants from reactions that occur because of the sunlight, as well as other chemicals present in the atmosphere. And so let me show you guys have probably seen like pictures of like, for instance, like Beijing. They have a very thick layer of smoke in the atmosphere for them, or maybe potentially like Los Angeles during sort of peak traffic times. One sec. Fog. There you go. Thank you, mate. Thank you. It's a smoke and fog together makes fog. There we go. It's funny. The funny part of it is that I learned what smog was from Nickelodeon. I remember that very distinctly from when I was a kid, but that means nothing for what we're talking today. Now, how does smog form? Again, it's a mix. It's some reaction that has to occur in the atmosphere for it to occur. It's typically catalyzed by the sunlight. Now, sun is a pretty big part of chemistry, just doesn't know. So we can sort of see what's going on here. Now we have what's called a thermal inversion, where we have cooler areas in the bottom, and then we have cooler areas at the top, and as we're going up in altitude, and then we have polluted air that comes up, and we have this inversion layer where things are getting really, really warm above cities, and it causes the pollution essentially to get trapped and accumulate in the area. Thus, we start to see areas of smog forming over large cities. So kind of a cool thing. But again, secondary pollutants occur because they react with it. Now, there's lots of things that occur. Lots of things that are considered secondary pollutants. They're chemicals, so they wouldn't really mean too much to you guys. But again, just know there's lots of secondary pollutants up there. Now, there's a really cool reaction that happens and a really important part of our atmosphere that I briefly mentioned, which is called the ozone layer. Now, our stratospheric ozone layer actually is one of the most important parts of our atmosphere. It's very, very thin. But ozone is really cool because ozone actually basically captures ultraviolet light. Now, for those of you that are like me and you're very fine-skinned, you worry about sunburns when you go out on a hot day. Now, why do you worry about sunburns? Well, what causes a sunburn? Well, you have the sun's rays come down. Now, most of the sun's rays are harmless, but there's parts of the sun rays, ultraviolet light or UV light, that basically hit your skin. Now, if you're from more, let's say, a Mediterranean region, or you have darker skin, that ultraviolet light reacts with your skin, producing melanin, giving you a tan. Or if you're like me, that UV light comes in, hits your skin, kills your skin cells, giving you a sunburn. That's what a sunburn is. It's just your dead skin. That's all that's happening there. I know that sounds terrible, but that's what a sunburn is. Now, that would happen far more frequently if we did not have our ozone layer, again, which is very, very thin layer of gas. Now, what happens is the ozone layer, ozone gas, which is O3, so 3 oxygens bound together. For those of you that have never seen that before, that's what ozone looks like. Ozone forms, just as a note, when oxygen in the atmosphere comes together, just as a note. Now, what ends up happening is that ozone, it will absorb ultraviolet light, preventing it from getting down to the Earth's surface. And it does this by breaking apart, forming O2 and O. But as we just mentioned here, O2 and O can react together to form ozone. So ozone absorbs ultraviolet light, breaks apart, and then comes right back together. It's kind of a really wild thing, but again, makes life on this planet possible. And we'll talk more about the ozone layer when we talk about climate change, but I just wanted to make mention of it. Now, one of the interesting things about the ozone layer is that in the 1970s, Lovelock, and as well as a scientist named Lovelock and Rowland and Molina actually discovered a group of refrigerants. They're called chlorofluorocarbons, or CFCs, were actually reacting. So they were just like making refrigerators cold. That's what they did. They were actually reacting with stratospheric ozone, causing it to essentially go away, thus thinning the ozone layer or depleting the ozone layer, leading to more UV light coming into our atmosphere. So kind of interesting thing, human activities directly affecting the atmosphere. And we'll talk about climate change because we'll talk about climate change in depth in terms of how we're affecting the atmosphere, because it's a really important part about climate change. The atmosphere plays a really important role in terms of climate change as well. Now, as I mentioned, these chlorofluorocarbons or CFCs are depleting our ozone, and we can sort of see this here where we have holes, some pretty severe holes in the ozone here, going on here. And we're showing a pretty steady decline in the ozone throughout the 70s and into the 80s. We can sort of see that here, some pretty large ozone holes going on here, here, and here. Pretty large. Now, the highest level of depletion, as you may or may not be able to see, is actually in Antarctica. So you can see Antarctica is here, and the ozone holes were forming over Antarctica. And actually, there was so much destruction of the ozone layer during this time. It was actually about a 50% reduction in the ozone layer over Antarctica. Now, it might not seem like a big deal because it's Antarctica. Nothing really lives there except for the cool penguins and some other stuff, but mostly just the cool penguins. Why was that a big deal? Well, the reality is if we continue to do what we were doing, it would lead to more of a global destruction of the ozone layer as opposed to this localized version that was happening here. Now you might ask yourself, why was it happening only over the Antarctic? Well, you got to remember back from our air currents, right? The CFCs were getting into the air and being carried to the Antarctic, and that's where they were doing their damage. That was really what was going on there. Now, as you can see, pretty big. Remember, red colors here are always bigger, but you can see by 2006, the red colors are going away. And then by 2018, the red colors are actually starting to increase again. So we went from bad to really bad, and then not so bad, and now we're coming back to be bad again. Now, how did it go from bad to really good? Well, actually, it was a pretty important environmental treatise or treatise, whatever you want to call it, called the Montreal Protocol that was enacted in 1987. It actually phased out the use of CFCs, which led to the recovery of the ozone hole. But as you can see here, the ozone hole is coming back. You might ask yourself, what is causing the ozone hole to come back? And we'll actually talk about that at climate change lecture. But just to foreshadow it, it's a greenhouse gas called nitrous oxide. So keep nitrous oxide in your brain because it's going to come back, not just here, but it's going to come back during climate change. So that's the ozone layer. Now let's talk about a really interesting but relatively rare phenomenon called acid rain. Now, normal rainwater is slightly acidic. So if you think about what acidity is, like something that's very acidic is like lemon juice, right? So lower pHs mean more acidic, higher pHs mean more basic. So if you want something really basic, think about like soap, right? Soap is very, very basic. And so normal rainwater is slightly acidic. It has a pH of about 5.6. Now, in the 70s, we actually saw a rise in sulfur dioxide, SO2, as well as nitrogen oxides, NOx. NOx is either 2 or 3, one of the two, just as a note. Now, where were these coming from? Well, they're actually coming from human sources, car exhausts, industrial and the agricultural processes. And what these gases were actually doing, so sulfur and nitrogen, they were reacting with water in our atmosphere to form sulfuric acid, as well as nitric acid. And I know that sounds kind of, I don't know, maybe a little bit out there or maybe a little scary. I don't know. It seems kind of an odd thing to think about, but that's what was happening at the time. That's what's still happening now. And so these acids were forming in our atmosphere. They would collect in our rainwater and then precipitate down, leading to acid rain, or sometimes what's called acid deposition. Why is that the case? Well, again, these acids are forming in the atmosphere, coming down with our rain, leading to the acidification or the dropping of pH of our forests, of our aquatic ecosystems, of our oceans, leading to damage to these ecosystems. And you can sort of see this in this graph here, where you have damage to vegetation, right? The trees are dying off, but you can also see that the plants are getting sad and the fish are getting sad in this little pond here, or lake, or whatever you want to call it. But again, lowering the acidity increasing the acidity of our rainwater, leading to damage to our ecosystems. And we can actually physically see this here on a statue. So this is actually in Lichfield Cathedral in England. And you can see this acid rain has come down. It's eroded this statue of, I forget who it is. I don't remember, of this gentleman here, leading to damage to the statue. But that's just man-made structures. As I mentioned, it has pretty dramatic effects on natural systems. So we saw pretty dramatic changes of lakes and rivers throughout the New England and Canada and New York and places like that. Pretty dramatic changes into forests. making our soils more acidic, affecting plant growth, all sorts of different things, leading to pretty dramatic changes in our atmosphere. As I mentioned, acid rain is pretty common. It still happens today, but is significantly less common than it used to be as we regulate air pollution more and more. Now, there's actually a pretty cool thing. Acid rain doesn't affect all landscapes equally. It's actually kind of a cool thing. Now, in the Midwest, most of the soils in the Midwest have a really pretty heavy layer of calcite from limestone, which actually helps them neutralize acid rain. Whereas in New England, we don't quite handle it as well because we have lots of bedrock that doesn't help sort of get rid of the acidic rain very well. But it's actually kind of a cool thing. So a couple of years ago, I went to Mackinac Island in Michigan, and they have this really cool formation called Arch Rock. It's about 146 feet tall, and you can see the effects of acidic rain, both natural and man-made, on this arch here, because this is a really nice limestone arch here. You can see this monstrous hole in it. And how did that occur? Well, again, it was acidic rainwater coming through, carving a hole through this rock, creating this really beautiful arch here. If you guys have never been to Mackinac Island, it's a pretty cool island off Michigan. You can only get there by boat. There's no cars there. You can only like bike around and walk around. So it's kind of cool in that thing. But there's this really cool arch there. Again, showing how different soils, different areas of the world handle acid rain better than others. So kind of a cool thing. So that's all the different things that come to be issues with air pollution. That's how the air works. That's how weather works. So let's talk about some how we respond to air pollution, because clearly air pollution is still a problem. Air pollution has been a problem since the Industrial Revolution. So what are some of the ways we deal with air pollution? And I'll just preface this by saying on your average everyday year, about 9 to 10 million people die because of air pollution prematurely. So air pollution is no joke, and it is certainly projected to stick with us for an extended period of time. However, the United States did have the Clean Air Act. Now, parts of the Clean Air Act were eroded by the previous administration, just as a note. But the Clean Air Act was established in 1970, and it established two things, the first being air quality standards and the regulations on the source of the pollutants. And you can see all these different air pollutants from the 1990s to close to modern times, and you can see a decline in different things, whether it's lead, carbon monoxide, nitrous oxide, ozone, so on and so forth, all decline in these things over time due to better regulation, as well as the regulation of the source of those pollutants. So regulating factories, regulating cars, things of that nature has led to a pretty dramatic decrease of our air pollution. But again, air pollution still is a pretty big issue. And I think the one that sort of underscores this the best is actually lead. You can see lead here in dark blue, and it's got its own little scale over here. Lead levels were pretty high, and then after the Leaded Air Act that was enacted in the early 90s, we see about a 1,300% decline in the amount of lead in our air. So pretty successful. Air quality regulations have been very, very good, but they are clearly not uniformly enforced. And just as a note, like you can really see this, for instance, if you go to Michigan, they basically have the bare minimum for air quality regulations in Michigan. But then if you come here to Massachusetts, where we have very, very high regulation on our air quality, the air quality here in Massachusetts is way, way better than it is in, say, Michigan and other states that have different levels of air quality control. The South does a really bad job, whereas the North, California, Colorado does a much, much better job at regulating. But there are minimum standards. The minimum standards are crap, just as a note, but they have led to some pretty strong reductions. Now, there are acceptable levels of pollution, because there'll never be no pollution as long as we're doing things the way we are. So there is acceptable levels, including how much time they hang around and what levels they should be. So for instance, lead should be less than 0.15 micrograms per meter squared. Meter cubed. There should be X amount of particulate matter and so on and so forth. So there is acceptable levels, just the way there's like acceptable levels of like bug parts in your peanut butter and stuff like that. But lower levels obviously are the best, right? Always the best. Now, the Clean Air Act of 1970 was great. It gave the EPA the power to set emission standards for more than 70 categories of pollutions, and it has done a great job. It has saved millions of lives since it was enacted, prolonged the lives of Americans by about 4 to 5 years. So it was a really, really great thing. So if anyone tells you the Clean Air Act hurts business or anything, or it's bad or anything like that, it's just stupid. It's one of the most successful environmental policies that we've ever enacted. But in 1975, we actually had the Energy Policy and Conservation Act, which was actually put forth by the Department of Transportation, which actually set minimal miles per gallon, or MPG, standards for cars and vehicles, as well as light trucks. And there's also they also set what we call CAFE, or corporate average fuel economy standards, as well. And you can sort of see this over time, where we can see the miles per gallon, the year, and you can see steadily we see a rise in the amount of miles per gallon of our passenger cars. And we sort of see a stagnation through time, but again, it has been going up in recent years as well. And we can see it on industry standards as well. Industry standards have seen it go up, plateau for a bit, and then it's continuing to rise. But again, all thanks to our friends at the EPA, as well as the Department of Transportation, setting minimum standards of air pollution, fuel economy, which are directly tied together, right? Better fuel economy means less air pollution, right? That's just how it goes. Now, we've done some other things. Now, in 1990, we actually had some amendments to the Clean Air Act. We added what's called the Tradable Emissions Allowance Policy, which actually, where the EPA could set total allowable annual emissions for pollutants from utilities, which then divided that total pollutant into tradable units called allowances, which can be bought and sold. So if you're a really, really green company, you can sell the bad things that you don't do to other countries, so other companies, so they can continue to do bad things. Great way to get people to reduce emissions, but also doesn't really do a great job of regulating large businesses, but it does a pretty decent job. So this is one of those cap and trade systems that I mentioned during the public policy lecture. So it's a pretty decent thing. I would argue it's probably not the best thing, because it still encourages pollution. But if you can get people to be more conscious about not polluting, if they can save some money or make money, then it's not a bad way to go. Now, the cumulative benefits that it's actually been estimated by the EPA of this policy, so the Clean Air Act and the Tradable Emissions Allowance Policy, was estimated to be worth about $2 trillion to the U.S. economy over about a decade or so period. So it is a very valuable economic tool for businesses and things like that. Now, there's some interesting things that are going on. Air pollution in China. I figure I'd just make mention of it because it's kind of a cool thing what they're doing in China. Now, China, as you guys probably know, really, really heavily industrial nation. They have lots and lots of air pollution, lots and lots of coal-fired power plants. But I'm sure you guys probably saw when the Olympics were in Beijing a couple of years ago, Beijing went from a scenario like this. They stopped all car traffic in all of Beijing, pretty much. And Beijing went from this to this. And you can see this is a bad day in Beijing and a good day in Beijing. But again, this was the effect the Olympics had on air quality in Beijing. Now, in 2015, the Chinese government actually did issue its first red alert for hazardous air pollution in Beijing, which actually was just a regular occurrence there. You see pretty commonly in Beijing and across China, where it's pretty industrialized, people wear masks all the time because air pollution can be particularly damaging there. Now, the WHO did do a study that actually found that 1 million people died each year in China alone from the polluted air because of all their rapid industrial growth. It's kind of a crazy thing how, China's got a huge population, but how damaging it is to the health of people that live in China. And so it's kind of a cool thing to sort of see how air pollution can get out of control in an area where, again, you can see a visible difference between good and bad days, or the Olympics is there or the Olympics is not there. Kind of a cool thing. So the question is, and we'll sort of end here today, what can you do? You can make some differences in air pollution. choosing a more fuel efficient car, changing to more public transportation, things like that, limiting how much energy you use, right? Because the more energy you use, the more pollution you produce. But pollution is kind of a big problem, sort of universally across the planet. And it really requires a meaningful switch away from the consumption of fossil fuels. Until we really switch away from fossil fuels, no matter how much an individual does, it's really not going to matter in terms of the global budget of the planet in terms of pollution. There just really isn't. So until we sort of move away from fossil fuels, what the individual does for pollution really doesn't matter all too much. But if you do want to sort of see, you can improve your energy efficiency and things of that nature. But again, it's really more of a systemic problem as opposed to you as an individual need to fix air pollution. So, all right. So that's going to be it for the day. Let me stop recording. So if you guys have any questions, I will